Okay, we'll pick up here, which is the next slide after the example gauge reading. This one. There's just a slide about blood pressure and 130/80. The units for that are different than the units that we discussed earlier for pressure. It's not pascals, it's not bar, it's millimeters of mercury, as like in a barometer, a mercury barometer. So 130 millimeters of mercury, and we can go look up the conversions to pascals or whatever other unit you like. Blood pressure varies with vertical position in the body because the equation for that represents Pascal's principle that pressure increases with depth in a fluid. So our blood pressure should, I think, be greater in our legs than in our arms because, well, at least when we're standing upright, because we are, well, that fluid is deeper in the column of blood than the blood in our arms. So the next principle we need to talk about, we just now talking about Pascal's principle, we imagined a square area of fluid on which the net force must be zero. What if there were an object submerged in the fluid? And we've said that ice floats in water, and I guess that was back when we were talking about density. So the fact that ice has a density less than water means that it floats, but why does it float? And, well, the water holds it up. Well, okay, how, why, and how strongly? What is that force that pushes up on an object other than fluid, submerged in fluid? And that's why we need Archimedes. Now, we can tell the story, the apocryphal story of the ruler receives a gift of a crown from a neighboring, region, and hands the crown to Archimedes, this scientist in residence, and says, "Here, make sure this is gold. If it's not gold, then they lied to me, and I'm going to go attack them or something." And so the issue, Archimedes can measure the mass. He's got things of known mass, whatever the standard was for the day, and he has a balance, and so he can figure out what the mass of the crown is. If we can calculate its density, then we can, because we know the density of gold. But the trouble is, there's no good way to find the volume of, a crown with all the, ornaments and things that go onto it. If we had, if we had a function that represented all of these little doodads and junk on the top, then maybe we could integrate, but we haven't invented calculus yet, so I'm not really sure how we're going to find the volume of this crown to find the ratio of mass to volume and say, yes, it's gold, or no, it's not. And he's, Archimedes is frustrated by this, and he spends all day in the lab, and he's getting, madder and madder that he can't figure it out. And he says, you know what, screw it, I'm going to go take a bath. So he goes to the bath in the city. Well, it's a public, bath, bathhouse, I suppose. And but he's got his own tub. Like, he doesn't have to share because he's the scientist, right? And he's got his own bath butler, right? Like his own attendant, and It's okay. I'm Archimedes, and I want you to fill up my bath to the brim, right to the edge. And he gets in the bath, and we know that some water spills out, and he jumps out of the bath and shouts "Eureka!" um, which is a pretty literal translation for "I got it," and um, runs, well, in the story, runs naked through the streets of Athens to back to the lab to leverage this idea, the principle of displacement. That if we submerge an object in water or some other fluid, that it the object pushes aside a volume of fluid equal to the volume of the object. In other words, that only one thing can take up this space. The volumetric, the spatial extent of this object pushes aside the water that used to be, or the fluid that used to be in that space, and we say that it's displaced. And if you Google a little bit, you might see Archimedes' principle explained as just displacement. But Archimedes' principle is cooler than that. And Archimedes' principle has to do with the force from the fluid that supports a thing submerged in it. Why does the ice float? Something must be holding it up against the force of gravity, and it's the fluid itself. It's the pressure. It's the force that the fluid exerts. But we know, because of the principle of displacement, Archimedes can show how strong that force is. Suppose we have a beaker of water, and we have some imaginary chunk of water that we're talking about. This is some weird little potato-shaped thing. That much water within the other water. That much water has a weight, and gravity pulls it down, but it doesn't move because the fluid at rest just doesn't go anywhere. It just sits there. So we know the acceleration is zero, the net force needs to be zero. And the net effect of all of the different pressures must be an upward force. Because there needs to be an upward force to cancel gravity. That's okay. We kind of expect that because this point in the fluid is not as deep in the fluid as this point. So those two forces are diametrically opposite and would cancel each other if they were the same strength, like they were a few slides ago when we were talking just about a sheet of water as opposed to a potato of water. But now the bottom of the object is deeper than in the fluid than the top, and therefore the pressure and the force exerted on the bottom area is slightly greater than the force exerted on the top area. A net upward force enough to hold that potato of fluid at rest vertically. Okay, this is fine. What if we replace this potato of water with a potato of potato? with an actual thing, something that isn't water? Well, that's fine. This thing pushes away water, pushes the fluid away and takes up the space. It's like we remove this potato shape of fluid and replace it with this potato shape of not fluid. Replaced, right? So there's no additional volume we need to take up. We replaced the thing we had with a thing of equal volume, so there's no change in the rest of the fluid, which means the rest of the fluid is behaving exactly like it was a second ago, that there is the same amount of net upward force on the real potato as there was on the imaginary potato of fluid, because we haven't changed anything about the environment in which it lives. The bottom of this volume is exactly as deep as it was a second ago, and the net pressure on the bottom is, the pressure on the bottom is more, and the pressure on the top is a little bit less than that. So the net pressure is still an upward force, equally strong as it was a second ago, because we haven't changed the environment. We just changed the object on which the forces are acting. We replaced this potato of fluid with a real potato, but that potato exists in exactly the same fluid environment as it did a second ago. So the forces acting on it as a result of that environment must be the same. We know how much force that was, though. It was a force equal to the weight of this much fluid, because it had to hold it up against gravity. That the net force needs to be zero because it doesn't move. So this upward force, the buoyant force, must be equal to the weight of this much fluid, which means this object is also subject to exactly that much buoyant force because it's living in exactly the same environment. The object submerged is subject to a upward buoyant force equal to the weight of the fluid that is displaced by the object's volume, because this object is taking up volume that this fluid was taking up. If we displace it, allow it to like spill over the edge of the cup, then this is where we are. That the net buoyant force on this object is the same as the net buoyant force on an equally sized region of water that we replaced with this object, because the fluid environment for both is the same. A completely or partially immersed or submerged body is subject to a buoyant force equal to the weight of the fluid displaced. That's Archimedes' principle, not the principle of displacement. That's another thing, and really that's like a sort of a conservation of space almost. Like, well, if you're taking up space, you're taking up space. Archimedes' principle has to do with the upward buoyant force acting on a submerged object. Okay. That's Archimedes' principle. And I'll stop this segment there. The next thing we've got to talk about is Bernoulli's principle. And for Bernoulli's principle, we've got some slides that we need to talk about, and then there will be a derivation on the